So, hello everyone. So again, we are going to discuss a force method example using how to use how to form the primary structure using a hinge. So we did uh, a similar example before, and this is three span beam, right? So we know the first thing is if it is using force method, we need to know what is statical indeterminacy, right? So we have in reaction here, right? Two reactions called RA and HA. Here you have RB. Here you have RC. Here you have RD, right? So since you don't have any horizontal loading, right? So you can assume this HA is approximately 0, right? Then you cannot use even the horizontal force equilibrium as well, because no horizontal forces, then you can use that equations as well. So that means you have originally you had 5 unknowns and 3 equations, but now this becomes 0, then 5 becomes 4, and you cannot use even the horizontal equilibrium equation. So equations becomes also 2. So again, your statical indeterminacy remains 2, right? So this is very simple. So today I'm going to so for at A and D, right? So the bending moments are 0 at the free ends, right? But and B and C, bending moments are not 0, but sigma m is 0, right? Opposite and equal in both sides. So if you just draw the bending moment curve, so it would look like this, right? So here from both sides, hogging moment, right? So we are focusing on one part, right? If we know this part, it is equal to the bending moment on the other side, right? The equal and opposite. So here, statical indeterminacy 2 means you need to remove 2 redundants. So the best way is, if you are using force method, you can remove RB and RC. Then it is going to be simply supported beam, and you can solve it. But that's not easy, right? Just see, your first coordinate is this, second coordinate is this, if you consider, right? So then it would be something like this. You need to apply a unit force here and check the deflection here. So this equation, put it into the equation, and simplifying it is not easy, right? It takes time, right? Than it is supposed to, right? So in such case, best way is to form a hinge, right? So that means we are not actually removing any redundant, but we are, so literally we are setting this bending moment to 0, so that we can take bending moments. So we can separate each part into 3 spans like we did before. It's relatively rotated, right? So here it's beam continuous, relative rotation is 0, relative rotation is 0, right? So think about the term, it is relative rotation, right? Compared to this part will not rotate relatively still. If you form a hinge, it can, right? So that's what we are going to do, right? So we are going to, okay, so we are going to say the primary structure like this, right? So L is equal, okay. So we are forming a hinge here, right? We have loading here. So not that QL is equal to W, because it's easy for you to simplify them. Otherwise, Q and W, you can't simplify the answer, right? So this part, so if you provide a hinge, just like we did in the last example, it can move, rotate separately, right? So we don't know whether it can be large or smaller than this deflection, but we know this is exactly equal to the first span, right? So this is span. So if I call this theta, this is also theta. Here is also theta. Here it's also theta. Right here, I would say alpha. We don't know, right? So first mark the, so I don't have enough space to draw the primary structure and the redundant structures in the same side. So I will move it each at a time. So this is my first coordinate, redundant, second coordinate. So my clockwise positive and upward positive. Okay, that's my sign convention. Okay, clockwise rotations and forces, that means moments. So upward forces and displacements, right, are positive. So what I need to know is, right, so what I need to know actually is, I can go ahead, and so the required action, so first we write the force you need, right? The force matrix you need is MB and MC. So the required actions, it's called RA, RB, RC, and RD. Okay. So those are my actions and the forces I need to consider, right? Okay. So we need to know, so this is our primary structure, right? So at each step, you need to consider, so in the first method, we consider the displacement and the actions, right? So to find the forces first, right? So the displacement matrix we can write here D1 and D2, right? At each step, we need to find this matrix and this action matrix correspondingly, right? So D here is the relative rotation, right? So it's here, you consider this again theta, this is alpha, right? So the relative rotation is theta plus alpha. Compared to this part, the right hand side has moved clockwise direction, right? So that's positive theta plus alpha. Here also positive alpha plus theta is the same as theta plus alpha, right? So we need to find these two in using the appendix, right? So let's go to appendix, and here you can see you have given q, so you need to find f4 or f5. So both are equal. So those are ql cube over 24 ei, and we can take it, and from here you can set. So p is at the middle. You need to know f2 or f3, right? So if P is L over 2, right? F2 equals to F3 PL squared over 16 EI, right? PL squared over 16 EI here, QL cube over 24 EI, right? So we can go ahead and write theta is QL cube over 24 EI, and alpha is WL squared over 16 EI. So you can take one L from this to QL, and you can write instead W, right? So you can write theta again. W L squared over 24 EI, right? So now you need to just just add alpha and theta, right? So your common term is 48 EI, so it is 16 into 3, right? So here 24 into 2, so it's gonna be both 5. You can take, okay, that's okay, you can take it out, 5 WS squared over 48 EI. Okay, so now you need to determine the actions as well. So how to determine the actions? Okay, so now there's a hinge, right? So you can separate those. It's just like simply supported, right? Yeah. So actions, you need the vertical reactions, right? So here it's QL over 2. Here also. Here it's W over 2. And here it's QL over 2. So QL is W, right? So you can write this as again W over 2. So this is W over 2, right? This is W over 2. This all thing going to be W, right? This W over 2. W, 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 W. So this is W over 2, right? So your action matrix, action of the primary structure is going to be W over 2, W, W, and W over 2, right? So now my primary structure is done. So you need to apply the first redundant. So how we are going to do that is so again go here, I can delete this. Okay, so now I can draw my structure with the, okay. So I need to give the first redundant, right? So I remove the, so my first coordinate is at B, so I remove the moment, so that means I make it 0 by introducing a hinge. So I need to give a unit moment in the clockwise direction since it is so there's a hinge. Okay, so I need to give the exactly, because I need to worry on this part. If I know this value, that is exactly same to this value, right? Okay, so uh, if you apply a unit moment like this, right? So your beam is going to deflect in this fashion, right? So it's not symmetric within a beam, but the shape is exactly similar. So this beam is going to remain as it is. It does not have any effect, right? So since you already have a hinge here as well, so you can determine these values. So I call this alpha. This is also alpha, right? But this is not alpha, this is beta, I would say. This is also beta. So the relative rotation would be here, also alpha. Here compared to this part has relatively moved beta in clockwise direction. Okay. So that is displacement actually, right? So because we are again and again checking the compatibility of the structure, shape of the structure at these two coordinates, right? So here we got the displacement, right? So now we need to know what is the force, displacement for a unit force. So we call it the flexibility, right? So the flexibility at first coordinate due to the force at the unit redundant at first coordinate, right? So next, the flexibility, the displacement at uh, sorry, the second coordinate due to the force is still at first coordinate, right? So this is the flexibility coefficient 1, 1. So which means the displacement at first coordinate, right? First coordinate due to the redundant at first coordinate, the same location, right? So this is displacement at second coordinate, right? Due to the unit redundant at first coordinate. So this would equal to, this is equal to, so this is 2 alpha in clockwise direction. Compared to this part, this has moved 2 alpha in clockwise direction. So that is 2 alpha. This is beta. So how to take this alpha? So using appendix, you can write this equation. So if you apply a moment, you can see alpha is F1 ml over 3EI. So m is 1, right? And the far end is ml over 6EI. So keep it, remember. So alpha is, so those are again near to the applied moment. So that is 2 into ml over 2EI. So m is 1, L over 3EI, right? Sorry, 3EI. And the beta is, so it's the far end, 1 beta, just 1 beta, L over 6EI. Why our m is gone? Because m is equal to 1, right? Okay. So yes, it's done. So now we need to find the actions as well. Action. So my action coordinate is different, right? So AU so my action coordinate, this is 1, this is 2, RB, this is 3 RC, this is 4, right? Action at first coordinate, second coordinate, third coordinate, action unit, okay, U, fourth coordinate. Due to the unit redundant at first coordinate, again first coordinate, first coordinate, first coordinate is equal to, right? So if you apply a moment like this, so you can take bending moment about this point to this half. So that's going to be anti-clockwise moment 1. So you need to determine RA. So I'll call it VA into L is equal to 0. It is 1 over L, right? If it is 1 over L at 2, it's going to be minus 1 over L by considering the vertical equilibrium of this part, because from the hinge you can separate it, right? So this is minus 1 over L, and it will have another minus 1 over L from this part as well, right? So here 1 over L minus 1 over L. From the other half also it will have minus 1 over L, and here as well 1 over L. And the next part it's 0 and 0, right? So it's all gonna be minus 2 over L. So here 1 over L, 0, right? Now my displacement, so the flexibility is done, actions are done. So first coordinate is okay, and I go ahead and apply a unit redundant at the second coordinate, right? So if you apply like this, it will be like this. The same fashion, right? This is alpha, this is alpha, this is beta, this is beta, right? So my flexibility coefficient at, this is my first redundant coordinate, this is my second redundant coordinate. Okay, so flexibility at first coordinate, flexibility at second coordinate, right? Due to the unit redundant at second coordinate, due to the unit redundant at second coordinate. So that is just displacement per a unit force. Here actually the rotation per a unit moment, right? So the relative rotation again. So compared to this part, this beam has moved the original part. This, so hinge is there still. Compared to this location, so you can extend this part, original part. So compared to that, this has moved clockwise direction beta, right? This has moved clockwise direction 2 alpha. This is also alpha. So you can see the same, right? So because the redundant forces are same, right? So the similar manner, alpha value is also same, beta value is also same. L over 6 EI. So once I told you F12 should be equal and exactly equal to F21. Okay. Otherwise, you have made a big mistake. 12 over 3 EI. Right. So we are done, right? So yes, we can go ahead and find the actions as well. So action unit. So at, this is my first, sorry. This is my first action coordinate, second. So I'm using different colors so that you can understand it easily. So action at first coordinate, second coordinate, third coordinate, action at fourth coordinate. So this is u, okay. So due to the redundant at 2, so it's gonna be the same, right? So you can see this structure arrangement with this unit moment is same as this, right? So you can expect the same forces. If you have a moment like this here, it's going to be a moment here, right? So exactly flipped, right? So here it's going to be 0. You have nothing, right? Here it's going to be 1 over L. Here it's going to be minus 2 over L. Here it's going to be 1 over L. If you want, you can just separate and see. You have a unit moment of 1. So you will see this is 1 over L. This is minus 1 over L. This is also minus 1 over L. This is 1 over L and 0, 0. You can just take a bending moment about this point to this beam and find this value. Then consider the vertical equilibrium and find this value, because these two forces are the only acting in vertical direction. So similarly, you can do that. Okay. Yes. Now we are okay. So these are for a unit moment. So we need to multiply everything necessary by MC. That is the actual value. Here these are for a unit moment. So you need to finally multiply these things by MB, because that is the actual value, right? So if you know the displacement for a unit force, you just need to multiply it by your force, right? So simple as that. So for the the original structure, you know the relative displacement. We are taking the shape of the structure, that is compatibility. And you know this is continuous. So the relative displacement, relative rotation is 0 at B and C, right? From the primary structure you obtained, it is this, the relative displacement. It's 5WL squared over 48 pi. One and one plus at B you have, so again we just need to only consider this bending moment because it is equal. Okay, I did not consider this. So it is F11 into MB, right? Plus from the second structure you have F12 into MC. Right. So you can write the second as well at C, F21 into MB at C. Yeah, beta into MB, L over F21 into MB. And F22 into MC. right? So you can write this part as a matrix. So you can take everything out. Into MB and MC. So this is we called flexibility matrix into force matrix, right? So we just need to, so 0, 0, five, into 1 and 1 is equal to, so you know the matrix, you can just plug the values. So one last thing. So this is anyway a symmetric structure, right? Load is at the middle, right? Everything is geometry is symmetric. So what can you say about MB and MC? MB and MC are equal, right? So for this case, if this W is somewhere here, MB would be different from MC, right? It's not symmetrical. So here you can just write instead of MC, and you can just write MB and MB because MC is equal to MC, right? So you will see, if you simplify this, you will get two equations, but both the equations are the same. So that means this is just a linear equation, right? You can solve it using one step. You can take this to the other side. So 2L over 3EI into MB plus L over 6EI into MB. So that's going to be MB into, so 6EI, 4EI, 5L over 6EI, right? So 5 is getting cancelled, L is getting cancelled, EI getting cancelled, 8. So MB is going to be, it's going to be how much? Minus WL over 8. If you write it using Q, Q is W, QL is W, so that's going to be QL squared over 8 negative. So that negative sign indicates actually the bending moment is not clockwise, but it's anti-clockwise right here, right? So we took clockwise positive for this part. So that means the other half, it's anti-clockwise Q, anti-clockwise, the same bending moment. We only just considered this one, right? So we obtained this is negative. So that means here it's anti-clockwise, right? So once you know F, you can go ahead and find actions as well. So you can write RA is the action matrix. So action in the primary structure, what was that? W over 2. W, W and W over 2. Right. So the action unit matrix is 1 over L, 2 over L, L. So here it's going to be the force matrix, right? Force is MB and MB again minus WL squared over 8. If you take it out, so the force matrix was the MB and MC, right? WL over 8, sorry. This is. So how did this came, right? You know, this is action matrix. This is actions in the primary structure. Same way we took the displacement, right? Action unit matrix. And this is force matrix. So if you found this, so there are two steps, right? First, you determine the delta. So we check the compatibility of the original structure is equal to the shape in the primary structure, right? Into F into force matrix, right? So then actions is equal, action in the primary, sorry, original structure is actions in the primary structure plus unit actions into F. This is capital F, right? So you go ahead. So you know this is 0 because relative rotation was 0 for the rotations we considered, and we found this, and we had to solve this, and we solve it and plug it back to the second equation because we know this, and we know this. We can calculate this. That's what we are doing here, right? So this part is remains same, so we can write this. It's 1 over L so I can give this L into inside, right? So I'm putting this L to inside, right? then L is getting cancelled. So it's just then L into 1 over L into 1 plus 0 plus everything 0. It's going to be positive 1. Right. So here it's going to be L is getting cancelled if you multiply it by L. So 2 minus 2 plus 1. So it's going to be minus 1. So here also minus 1. Here also plus 1. So you can see this matrix is also symmetric. RA equals to RD, RB equals to RC. If you want, you can find it that way. Yes. So you can take W over 8 out. Why? Here also W over 8 out. That's why. If you take 8 out, so this is going to be 4. This is going to be 8. This is going to be 8. This is going to be 4. So your final answers would be, so W over 8 into 4 minus 1. I'm taking W over out, so there will be minus 1 remaining here. 4 minus 1, so that is 3. 8 plus 1, so that is 9. 8 plus 1, so that is 9. 4 minus 1, so that is going to be 3. So your RARB, so your action matrix would be 3W over L minus, not minus, this is 3W over 8. This is 9W over 8. This is also 9. So finally 3W over. Okay, if you want, you can substitute QL instead of W. So that's going to be 3QL over 8, 9QL over 8, 9QL over 8, and 3QL over 8. Right. So yes, we are done. So these are also positive, right? So we considered clockwise positive and upward forces positive, upward forces and displacement. So these forces are upward. That means, so these are ended up as positive. So that means all the reactions are positive in the upward direction. And the moment we considered is negative, and that means anti-clockwise. So thank you.